a solution in practice. So this time we've got a fairly large step size of 0.5, and I've got a derivative function f dash of x is equal to x plus y. So it just happens to be in terms of x and y here. Initial conditions, y equal to 0, x is equal to 1. I now want you to find out the function value at x equal to 3. So typically before now we might have solved that DE, okay, worked out our C value and then substituted in for x equal to 3. That's my exact solution. So even if you can do that, if you're asked to use Euler's method to come up with an approximate solution, you need to do that. All right. So here's my rule. The next y value is the previous y value plus h times the function value evaluated at the previous x value. All right. So let's have a look. X naught is equal to 1, y naught is equal to 0. They're my initial conditions. So by definition, y1 is equal to y naught plus h times f of x naught. Now, f of x is just adding the x and y values together. So that's what I'm doing here. I add the x and y values together. So x naught plus y naught is just, back over here to the left, is just 1 plus 0. A half times 1 plus 0 is a half. 0 plus that is a half, so y1 is equal to a half. So let's record that. y1 is a half. x1 is just x naught plus h, so the next x value, which is just 1 plus 0.5, which is 1.5. So there's my first iteration, okay, my first approximate value. At x equal to 1.5, y is approximately a half. Let's keep going because we have to get up to x equal to 3. So if I add 0.5 to 1.5, I get x2 is equal to 2.0. I've now got to work out what y2 is equal to. So y2 is equal to y1 plus h times x1 plus y1. Okay, because that's what the function is, x plus y. So x1 plus y1, if we go back to our values, was 1.5 plus 0.5, so that's 2. 2 times a half is 1. 1 plus a half is 1.5. There's my y2 value. And we continue to go through that process. All right. So step by step, if by chance we had to do it in a tech-free, 2 probably stops at 2 iterations. But fortunately for us, our CAS provides the necessary function to enable us to come up with the approximate values. So if we go to Euler, okay, under our catalogue, the syntax, if you like, is, so we have Euler, the function, which is the derivative, okay, and then you've got to list your independent and dependent variables, which are x and y. We then want, as a set, the set of x values you're interested in. So we want to work from 1, which was our initial x value, up to 3, which is the final one we're interested in, comma, okay, now what is, if 1 is my first value, what was the y value at that point? And that was 0, which is that 0 there. And then we have, okay, what's your step size, which is 0.5. All right, so it's the derivative, x, y, the set of x values you want to generate values for, your initial y value, which has to correspond to the initial x value, and then your step size. And you can see there's my set of calculations that match off to the points in between, 3.25, the 1.5 I had, etc. All right. All right, so if we have a look at another one, again, we have a derivative, dy dx equals natural log of x. We're interested from x equal to 3 to 3.5 using step size of 0.1, which is typically the step size we use. And we know that at x equal to 3, y is equal to 2. So if I come straight to my Euler CAS instruction, dy dx is natural log of x, comma x, comma y. I'm interested in the values from 3 to 3.5. And at x equal to 3, y is equal to 2, and I have a step size of 0.1. Close bracket, enter. And so you can see there, I haven't got the whole screenshot there, but some, say 3.1, 2, 3, 4, and 5. Okay, so we actually had to have all the values, didn't we? It didn't ask for a specific value, but at 3.5 we get there. So manually, you can see the calculation. So my first calculation, if we just sort of address that one perhaps, we know that at x equal to 0, at x equal to 3, y is equal to 2. So there's my x0 and y0. I've got a step size of 0.1, which means that y1 is equal to y0, which is a 2, plus step size 0.1 times the function at x0, which is a function at 3. So 2 times 0.1096 is 2.1096. We can just sort of catch the end of it there on our CAS. Y2 is the previous y value, 2.10986, plus 0.1 times the function evaluated at the next x value, which is 3 plus 0.1, 3.1. If we evaluate that on our CAS, we get our 2.23. So you can see straight away that you can't actually do this problem involving a natural log of x without your calculator. And if you've got your calculator, well, you've got access to the function to actually generate the values. All right, so some things to note. Euler's method gives a numerical solution to the DE, an approximate solution, okay? It will never give a general solution, but just give us a table of values for x. And these values for x that we've worked out, and we probably could have experimented and worked out what the exact values would be and compared them. They aren't obviously as accurate as the actual solution. So this information needs to be given to us, x0, y0, h, and h of x. All right? Yeah, and if by chance we have to do it by hand, construct a table. All right, there we go. All right, so a slope field is a tool that we use to try and come up with an understanding of what a function may look like for a DE that can't be solved. Okay, so typically something like that. dy dx equals x minus y over x plus y. So if we actually, all we look to do is substitute values in for x and y and just put little lines representing the gradient that you come up with at that point, and hence get a general idea of what the DE looks like, and hence perhaps what a solution curve may be. So we just put small straight lines or dashes at each point for x and y with the appropriate slope for the value that we get by substituting in. So for example, dy dx equal x minus y over x plus y, if I put in the point 1, 1, I get dy dx will equal 1 minus 1 over 1 plus 1, which is going to be 0 over 2, which is 0. So at the point 1, 1, I'm going to put a little horizontal line there because that's a gradient of 0. Obviously at the point 1, negative 1, there's 1, negative 1 down there, I'm going to put a vertical line because 1, negative 1 will give me 1 minus 1 on the bottom. And I get something, and so I'm going to end up with 2 over 0, which is undefined. So that's a vertical line. So we just put little slopes, little dashes, representing roughly what the gradient is. If we have a gradient of positive 1, we might put a little dash on a 45, negative 1, the opposite direction, etc. And we come up with a diagram of the possible values, or the possible curve, I guess. All right. So if we by chance had to sketch one, which is very rare, but maybe in a SAC, I would probably ask you to sketch one. We just do what we've done here below. All right, so we've got the DE, dy dx is equal to negative x cubed. Clearly we could solve this, okay? And if we solved it, we would end up with a quartic, wouldn't we? Okay, so negative 3, negative 2, negative 1, negative 0. So if I substitute values in, so for example, if I put 0 into this DE for any y value, okay, I'm going to get a horizontal line, which is why if we have a look, I've done a horizontal line all the way through there, because at x equal to 0, y equal to anything, I get a derivative of 0, a derivative value of 0. Okay. Similarly, if I put x equal to positive 1, okay, if I put x equal to positive 1, if I substitute it into negative x cubed, I get negative 1 as an answer. So all the way along, I've got a little line that's got basically a negative 1 gradient. Okay. Similarly, if I put x equal to negative 1, I'm going to have a positive 1 gradient all the way along. Okay. And in this case, because our derivative is independent of y, those values don't change at all. At say x equal to 3, I get a gradient of negative 27, which is really close to a vertical line. So my line's getting steeper. All right. So the slope field you can see there, if I just take off all the dashes that I've done. Okay, so there's my slope field. Now, what is a possible solution? Well, typically we just pick a point if we haven't been given a point. And so I've picked a point there between 1 and 2, and you do a bit of a sketch without crossing any of the slope lines. So you follow the slope field. So there's the gradients of the line just there, and you can see there, and it's not unlike our quadratic, our quartic graph. So it's kind of the graph that you would expect to get. Our CAS will do the same thing. If we go to the graph menu, put in a graph, go to the graph entry edit, the entry edit line, and then go down to select diff equations. Okay, and if you do that, you get this screen here. And what we're trying to sketch here, my derivative, dy dx, is equal to negative x cubed. And in this case, I put in an initial condition of x equal to 0, y equal to 1. And so there's a graph of a specific solution for that particular DE. All right.